So thank you. All right, we're going to be starting this session in about 30 seconds, so we can try to keep somewhat on time for lunch. And I will hand it over to Lisa Bucci to keep you in line.
Hey everyone, my name is Lisa. If you don't know me, I'm a hurricane specialist at the National Hurricane Center, and we're going to continue our talks on observations in tropical cyclones. And now we're shifting gears, talking more about their impact and use in models. So the first speaker we have today is Linus Magnuson from ECMWF, talking about observations in the EC.
Thank you, and thanks for the opportunity to present this work that I conducted together with Sharon Mayumda, Mohammed Dawi, and a lot of other people from ECMWF. Next slide. So most of this talk will be based on a manuscript that's currently under review for Quarterly Journal, and this will bring us back to the hurricane season 2020, where we selected a period from 15th of August to 21st of September, when it was quite astonishing hurricane activity and a couple of typhoons as well. And for this period, we run observation system experiments where we had our operational system as a baseline. And then first we had a number of data denial experiments where the first one was to withdraw all the observations within 4 degrees of each tropical cyclone. But then we also removed in one experiment all the microwave data, in another all the AMVs, and then all the GNSSRO with a special experiment with only the Cosmic 2 data withdraw, no Aeolus and no scatometer. But then we also run another set of experiments where we had data enhancements. So we have been striving to the all-sky assimilation, and here we added the all-sky assimilation of MSUA. We played around with the scatometer thinning. We also tried to assimilate the best track data or the position of the pressure minimum. And we also included aircraft data from the HDOBS dataset. So next slide. So what I found was a really good exercise was to actually just take one data assimilation cycle, see what we assimilated, and more importantly, what we not assimilate. So what you see in each black dot is a used observation, and each gray dot is unused. So here, for example, the thinning of the scatometer data is very obvious, and which led us to even play around with that setting. And if you in the bottom one compare the MSUA, which is clear sky, and the humidity sound, that's all sky, you can see kind of the impact of having a all sky assimilation. Next. And here's another set of observation types, and I think we have discussed it in a previous HFIP meeting. It's quite striking if we look at the atmospheric motion vectors, AMVs, how few we are assimilating in near tropical cyclone. During this period, we also had the Aeolus data available, which is now gone, but here you can see one line of sight a bit on the outskirts of the tropical cyclone Laura. Next. And here's the very final one, where we on the top see the impact of the inclusion of the aircraft data from the HDOBS for this particular cycle on the top. And on the bottom, you can see the type of observations that we got from using the best track data interpolated to be one observation every hour. If you compare the bottom left, where we only have buoy data, and buoy plus best track to the right. Next. So then the next one is when we have run this full period, we have all the tropical cyclones, how we're going to verify them. And what I'm going to present here is a comparison with the mean absolute error averaged over all cases, but after homogenization between all the experiments to make sure that we have all cyclones present in all experiments to be counted in the verification sample. We also use the frequency of superior performance to count how many times the experiment was superior than the control. So next. So this results in a lot of verification results, and what you see here is example is the scorecard we generated for position error. So first we stratified the cyclones depending on the intensity at the initial time. So we see the weak results for what was initially a very weak system on the top left, moderate system top right, and the strongest system, so initial winds above 32 meters per second to the bottom. And the black line in the middle of the scorecard is the division where we have the data denial experiments above the line. So here the expectation is to see red colors because we expect the forecast to be degraded when we remove the data. While if we are below the black line is the data enhancement experiments. So there we expect blue because we expect lower errors with enhanced. And you can see for the enhanced experiments is quite nicely come out with mainly blue. And I forgot to say the circles are the mean absolute errors, and the squares is the frequency of the superior performance. And if you look at the arrow that points to A, then you can see the impact of or the graded position forecast if we remove the data around within 4 degrees of the cyclone. So it shows that all the data on average making a good impact for the position. Otherwise, we see that when removing the microwave data, we have the most consistent impact on the grade in the position. Next. So then if we look at the same type of scorecard, but verifying the minimum pressure, we again see that removing all the data near the cyclone clearly degrades the forecast of the minimum pressure. So it seems like on average the data is doing good. If we look at arrow B, we can see, especially for the moderate systems, that removing the drop zones increase the error. So on average, the drop zones are doing a good job. But it's not so clear in the strongest system, which we will come back to. Then we see with arrow C that reducing the thinning of the scatometer data lead to better intensity analysis. And also, if we look at arrow E, including the assimilation of best track helps for intensity, while using the HD obs seem to be a bit more problematic for the intensity. Next. So look into the impact of drop zones and flight level data from HD obs for the 4 hurricanes in the sample. We here see the best track minimum pressure in black. Then the experiment that includes all the data types are in green. So that's the one we expect the best performance for. When we take out the HD obs, we go to the blue. And if we take out both HD obs and drop zones, then we get to the orange. And here we can see that for Tropical Cyclone Laura, it was problematic to assimilate this reconnaissance data during the most intense phase. So the green one is the one that is furthest away from the best track. While if we go to Tropical Cyclone Teddy in panel D, we can see that during the most intense phase, the orange was that didn't include any reconnaissance data was the most problematic analysis. The case that is murking up the water here is Paulette in B, where we see that the green that included all the data produced too strong cyclone during the intensification phase. But that was actually a little bit before the reconnaissance flight started. So it must be some randomness in the system caused by previous missions into other cyclones. But we can also see that when this cyclone or when the mission started, that it took some time for these experiments to converge back to what was the best track. Next. So here you see one example of the usage of the flight level data from HD obs for the U component of the wind for one data simulation cycle in Tropical Cyclone Teddy, where you on the left panel have observation minus the first guess, and to the right is observation minus analysis. And you can see on the top row the statistics for all observation and bottom for the used observations. And here you can see where we have very bright colors. We have large arrows, which you see especially on the top. But many of these observations were then rejected by the data simulation, which was in the area with the most intense wind. So it seems to be some problem to digest the data in the area with the most intense wind. Next. So to summarize the results, which were quite a lot and quite difficult to interpret in this paper, is that first that local observations are important, both for the position, but especially the intensity, which is reassuring because that's not granted in a global data simulation system that is constructed to work everywhere, every time. And that the microwave observations had the strongest impact among the satellites. But from single observation types, it was hard to see strong improvements or impact on the position. They reduced the thinning of scattermeters to improve the forecast. And then for the other types, we saw that the result from assimilating aircraft data was mixed, but HD seems to improve position forecast, especially for hurricanes. And on average, the drop zones improved the pressure minimum forecast. And we had some positive influence from assimilating the best track data. So next. So this brings us to the discussion, and we had a lot of discussion putting together this manuscript. And first of all, it's difficult to obtain a robust statistical results in a global system, and that's partly because of the resilience in the observation system. And then the effector resolution is a question mark, both for the outer loop in the and inner loops in the data simulation and the ensemble data simulation. And then that the results depends a lot on what type of observation error that we prescribed. And then the final of the discussion question is, why do we find a very different impact from the same type of observations when we look at the different forecasting systems? So when we look at the literature, what is found, for example, in the DFS. Next and final slide. So after this study, we have continued to work. So now we operationally assimilate the flight level data for an HD obs. The all sky M3 is an operation. We reduce the thinning of ASCAT. And we have also improved the resolution on different aspects in the data simulation. And we continue to test the assimilation of the best track data. So I'll stop there and taking questions in the discussion, I believe.
Thank you, Linus. Yes, we will hold questions until the end of our session. So if you could stick around till then, I'm sure people will have some questions. Next up, I'd like to invite Todd Hutchinson from Windboard to talk about observations and Windboard observations and their impact on models.
Great, thank you very much. I'm very excited to be here, and thank you for the opportunity to present this work here that on observations and impact of these observations in the GFS forecast system. I want to thank several people who did work on this project, including several at Windboard, but more importantly, those at NOAA, NOAA EMC, and NOAA COSAP, who have been working on this project with us for several years. So jump right into it. I've shared some of this information before, but I think, okay, great, thank you. Perfect. All right, so jump right into it. Very quickly here, I'm going to hit on some highlights on this slide, things that have, especially those that have changed since last year when I shared this before. Shown on the left there is one of Windboard's long duration balloons that flies for days at a time, typically days. Recently, over time, the average duration of these balloons has increased, and today it's at about 6 to 7 days. And the longest duration of any flight was 53 days. In the past several months, we had a very long flight. The key to the balloons and the long duration is not just the long duration, but the ability to remotely direct the balloon to ascend and descend. And I put a profile on the bottom left there to represent how that looks in terms of height. Ascending up to about 12 kilometers early in flight, or 180 millibars, and up to about 80 millibars towards the end of flight. And then down to typically 1,500 meters, but we sometimes push down to 500 meters, especially over the ocean surface. And I'll just state that there are some tests going on. I'll come back to this in just a minute to drop sons or sons off of the balloons from altitude. Okay, so focusing here on tropical seasons and specifically the Atlantic tropical seasons. We're going to cover the 2022 and 2023 seasons. Shown here are various flight paths during those seasons. During that period of time, Windboard was operating these balloons on a, I would say, intermittent process, meaning we would ramp up for field campaigns such as the tropical season. Since then, we've moved to more continuous operations, and that's what's shown on the bottom here in 2024, the continuation of the operations with time. And in 2022, we operated these flights, as shown on the right there, out of Cabo Verde and also Puerto Rico. And at the same time, a field project involving the what was known as the Thin Ice Program, sponsored by the Office of Naval Research, was going on in the Arctic, and we were flying there. So we had a lot of data at various latitudes during that season to assimilate into the models and assess the impact. 2023, generally in the mid-latitudes from South Korea, Palo Alto, California, and upstate New York in the Northeast US, typically staying in the mid-latitudes, but sometimes flying, dropping southward into the tropics, as you can see on the middle on the right there. Lots and lots of observations have been collected in these campaigns, on the order of, coincidentally, 353,000 in both 2022 and 23. And when I say an observation, what I really mean is a piece of the ascent that is about 100 meters, where we group the data that's collected in that 100 meters into a single observation and then assimilate it. And if the balloon happens to be traveling horizontally, we would group that into 30-minute buckets and assimilate and treat that as one observation for assimilation. And this, we're not going to see results from impact studies in 2024, but the data is available for future studies that we hope to do. And in 2024, this season now, we've flown about 3 times as much as the prior 2 seasons. I'll point out on this slide the launch sites, which you could kind of gather from the previous slide, but a couple things to point out here. Cabo Verde, I already mentioned. Guam, we actually operated late in the year out of Guam this past season. That's on hiatus right now, but we'll come back this winter. And soon we'll begin operating out of Western Australia in early next year. By the end of this year, we expect to have about 40 flights aloft at any given time, and that will grow in the coming years. And if we just take those sites and simulate some balloon tracks, this was actually just using GFS forecast data from 2022 and saying, where would they go? Nothing too sophisticated, but just to give a general sense of where 6 to 7 day flights would fly from these given sites. And you can get a sense of the coverage that's expected next summer and what we had this summer from those launch sites. Okay, I mentioned before some of the capabilities with dropsondes, and very excited to share these early results where we've been able to utilize some funding from the Weather Program Office, and we're very happy to apply that to the development of dropsondes here. What early prototype releases of these very lightweight sondes have occurred in California, where we dropped in the Central Valley of California from about 100 millibars. You can see on the top right there a SKU-T or data on a SKU-T showing a descent from high levels to low levels. Now, we might say, why would you want dropsondes on a balloon that can already go up and down? And there's a few reasons for that. One is, to begin with, collect more data is one objective. A second objective is to collect data all the way down to the surface. And even a third objective, which is probably the most important, is to be able to drop into areas of weather where the balloon typically wouldn't fly. For example, in precipitation, we generally avoid flying the balloon into precipitation because the extra weight from the precipitation can force the balloon towards lower levels and either decrease the life of the balloon or sometimes even force a landing of the balloon. And we recently did drop into precipitation in Hurricane Milton one sonde. So now these balloons are prototypes instrumented with one sonde. I expect that this winter we'll have many balloons, a large percentage have a sonde, and then in the coming year, next year, I won't say how many, but on the order of a handful of sondes per flight is what we're shooting for. Okay, impact studies, getting away from the sondes and back towards just the balloon flights themselves and the impact studies that have been done over the past couple of years. The first is in 2022, data was assimilated into the GFS forecast system. And the way that GFS was run at EMC was with and without windborne observations in a fully cycled manner. So it was as if it was operational, but retrospectively as if it was operational, but with the addition of the windborne data over the cycle by cycle, of course. What you see here in the upper right is a scorecard for the entire season in 2022, which is about 2 months. And the blue indicates a reduction in forecast error. Obviously, I don't expect you to read it, but the point is that there's quite a bit of reduction in error there, and it is statistically significant, as indicated by some of the bars on that chart. And it's modest. It's on the order of 1 to 3% at best, but nonetheless, in general, and for many parameters at many forecast lead times, a positive impact nonetheless. And that's for the broad scale parameters. If we look towards the bottom right of this slide, you see the average tropical cyclone error during the 2022 season was reduced when the windborne observations were assimilated. And we can choose, pick and choose, cherry pick, if you will, certain cases to find nice impacts, such as Hurricane Fiona in this case. So moving on to the 2023 season, there are 134 flights during that season, about the same amount of data as the 2022 season overall, although it was spread over a longer period of time, so a little bit less dense during that season. But once again, the tropical cyclone track error was decreased in the Atlantic. So again, a positive result, and it's nice to be able to replicate that over multiple seasons. I'm going to go a little bit deeper into some of those results. Just very quickly, I just wanted to show the slide to say that the observations are fitting better to or the analysis is fitting better to the observations after the assimilation, just to give the sanity check that it's doing the right thing. And that's passing, of course. And now diving into various domains for tropical cyclone forecasts. Starting on the left here is the Western Pacific in 2022. There was, you can see there, the with windborne in green, and the control, which was the operational GFS in, I guess that's red. An improvement in the West Pacific, neutral results, mixed results in the Eastern Pacific, and positive results in the Atlantic, as has already been shown. In the bottom is intensity as measured by wind speed. Pretty mixed results, really not statistically significant, though I would say in the Atlantic there was a positive impact, but once again, it wasn't quite significant. Still, it's still in the right direction, so happy to see that, that general result. 2023, continuing. Nicely in the East Pacific, or nicely in the Atlantic, we saw the results you've already seen. In the Eastern Pacific, positive, but not too significant. And in the Western Pacific, actually a degradation. So I guess not too surprising, we shouldn't expect positive results everywhere because there's so much variance from storm to storm and run to run. But in most domains, we have seen positive track improvement. Again, the intensity, very little difference in the forecast runs. Let's see where we're going. Okay, Hurricane Nigel. I just wanted to take one case and say what's going on, rather than to get a little bit away from the broad statistics and get a sense of how these observations are assimilated, and show you where they are when they're assimilated. So just took one case, Hurricane Nigel in the Central Atlantic in 2023, and we're going to look at one forecast, GFS forecast from Hurricane Nigel. Of Hurricane Nigel, excuse me. On the left here is what I call control, which is the operational GFS. On the right is experimental, which is the GFS with windborne observations. The gray line, thick gray line, is the best track of the system. On the left, the blue line indicates the forecast track of the control, and the red on the right is forecast track of the experimental. Pretty similar in terms of track, but you'll see the differences in just a minute. And in the upper, just over New England there, you can see the flight paths of the balloons, and there's some in the south and the Caribbean as well. The bottom left is the track error, bottom right is intensity error versus forecast lead time. So early on in the run, Nigel is through 96 hours. They're quite similar, though, as you can see there. And if we go to 144 hours, what happens? One of the reasons I picked Nigel was because I said we had some really nice statistics for this storm. And I said, well, what's going on? Why are we getting such a good forecast? Well, as it turns out, the cyclone is accelerating towards the northeast as the trough picks it up in the northern Atlantic and merging with that more synoptic scale cyclone to the north. The speed of evolution is what's really different across that path, or the speed of Nigel itself, and so that was a positive impact. If you look in the northern part in that synoptic storm, this at 120 hours here, or 168 hours, I'm sorry, made a very large difference, and likely a very large difference in the forecast downstream, perhaps in Europe after the merger of the two. So just to give a bigger view here and looking at 500 millibar, this is the same case, same initialization time. The windborne observations indicated by the stars on the map. The colors indicate the difference between the GFS forecast between control and experimental. And you see the dashed 500, the solid and dashed 500 millibar contours here, dashed being experimental and solid being control operational. At 0 hours here, of course, they're very similar. We move ahead to 24 hours, continues to be similar. Slight differences occurring at 48 hours, but as you'll soon see, they start to separate at 72 hours. And I'll quickly go through these. 96, 120, and there it goes. It's caught up in the trough. So what caused that? I don't know. It's hard to take a stab at it. These observations that are assimilated at this initialization time are of course important to which affect the flow, not only at 500 millibars like I've shown here, but at all levels. Also because the GFS was cycled, prior observations from prior to the initialization time also have an impact on the cycling and the initial conditions. So certainly a lot goes on, but there's ultimately, that's why we're looking at so many cases, but using one as an example to see what might be happening for the improvements. So I'm going to finish up there, and thank you, and please let me know if you have interest in looking at any of this data further. So
Thank you. All right, we're going to head back online to Sarah Ditchek at the Cooperative Institute of the University of Miami to talk about aircraft observations in the GFS.
Should I share my screen, or are you going to drive, Lisa?
We can do it either way.
Okay, I'll let you guys drive.
Okay.
That way,
Just
keep
let
my
us know
camera
when
on.
to advance.
Will do. Awesome. So thanks so much. So today I'm going to be sharing some results on the overall impact of aircraft recon ops on TC forecasts and GFS V16. Next slide. So to start, I want to give a snapshot of the project plan. Next. In our paper, Sippel et al. 2022, we quantify the impact of assimilating additional recon obs in GFS V16 on TC forecasts. And those additional obs included the first time addition of HD obs in GFS, as well as more drops on data in the TC inner core. But the overall recon impact still does need to be quantified, and that's where this project comes in. Next. To do that, there were two model experiments run, one that allowed recon obs called all R, and one that did not, called no R. And since no other differences were allowed, the differences in the model output highlight the impact of the recon. Next. So more specifically, recon assimilated in all R included drops as well as flight level HD obs, and in no R, naturally, no recon was assimilated. Next. Otherwise, both experiments assimilated all operationally assimilated conventional and radiance data. Next. So the experiments were run over periods of interest during the 2020 to 2023 North Atlantic Basin hurricane seasons, and this resulted in 710 cycles with 2370 individual forecasts for Atlantic Basin, East Pac, and West Pac TCs. Now, of the 107 TCs, 36 of them had recon, 27 of them were for North Atlantic Basin TCs, and so today I'm going to be focusing on just those North Atlantic Basin TCs. Next. So what you're seeing here now is the total number of assimilated recon obs in the sample. It's broken down by drops on the left, HD obs on the right, and both are further broken down by variable into QT and UV. So there were just over 1 million recon obs assimilated, around 80% of them being HD obs. And these values do include recon obs assimilated in any basin. So that does include 7 TCs in the East Pac, as well as 2 TCs in the West Pac that had recon. Next. So I want to give some more context to what the assimilated recon obs look like. And to do that, I'm going to be using Hurricane Idalia from 2023 as a representative example. Next. Now, again, HD obs accounts for the vast majority of assimilated recon obs in Idalia, and most of the recon assimilated was outside of the 250-kilometer radius. Next. So first, let's talk about the entire TC. So what you're seeing on the left is a map view graphic. This is the assimilated recon, and on the right is a corresponding graphic depicting how much recon was assimilated in each cycle. Reds are HD obs, purples are dropsons, and in total, all are assimilated over 56,000 recon obs during cycles of Idalia. 81% of those were from HD obs. And aside from recon within and around Idalia, you could see that recon aircraft were sampling another TC, that was Hurricane Franklin in the Western Atlantic. Next. So let's take a closer look at the cycle of Idalia that assimilated the most recon. Next. And in this cycle, all are assimilated just over 8,000 recon obs. These were mostly in Idalia, but some were in Franklin. Next. This is a distribution of assimilated recon by radius, both for the entire TC in dark purple and also for that one cycle shown above here in light purple. And you could see that on average, 65% of the recon obs are assimilated outside of the 250-kilometer radius. Next. So I want to give you a preview of what's coming up. Next, please. I'll be discussing results for, again, just the North Atlantic Basin TCs between 2020 and 2023, and variables discussed today are just going to be for track and VMAX, and that's because I'm going to be showing late and early model results. For verification, I'm using NHC best tracks following NHC forecast verification rules, and for analysis, I'm using my verification package GROUT. Next. So the main takeaways are as follows. While Recon directly improves track forecasts, it did directly degrade VMAX forecasts, and indirect impacts at long lead times also occurred. Next. So to see that pretty quickly, what I'm showing you here are track late model results for the full sample. This is using the consistency metric. Greens are improvement and reds are degradation. This is based on the consistency metric color bar on the bottom right. This metric's newly created metric. It applies thresholds to the MAE skill, the median absolute error skill, as well as the frequency of superior performance to identify consistency in results. If we only rely on MAE skill, it could lead to a misinterpretation of results if the sample is skewed, which it often is. If you want a lot more details on that, check out my recent WAP paper at the QR code on this slide. So as you could see, on average, there were minimal forecast impacts from Recon, but now let's stratify by Recon availability. Next. And in the first row, what you're seeing here, this is the direct impact of Recon on TC forecasts. And what that means is that this includes individual forecasts between the first to last cycle when Recon occurred for a given North Atlantic Basin TC. The second row is the indirect impact of Recon on TC forecasts. So in other words, the individual forecasts before and after Recon occurred, as well as from those TCs without Recon at all. So the results are showing that the Recon actually directly improved TC track forecasts at most lead times, while indirectly degrading track forecasts at long lead times. Next. Now for late model VMAX results, on average, degradation was found in the full sample in the first 2 days. Improvement was found on days 5 to 7. Next. But when we stratify by Recon availability, it shows that Recon directly degraded the VMAX forecasts at nearly all lead times, while indirect impacts were positive from days 3 to 7. Now, this degradation on days 1 to 2 is due to a negative intensity bias in the late model. This is corrected by the interpolator, as I'll show later on in the talk. But I do want to mention that these track and VMAX results demonstrates the importance of stratifying our samples by Recon availability when we conduct data impact studies. So for the sake of time, I'm only going to be focusing on the direct Recon impact results. Next. So overall, again, Recon directly improves track forecasts, but the magnitude and duration of the impacts depends on the post-processing procedures. Next. So what you're seeing here is mean absolute error, or MAE, on top, the associated MAE scale on the bottom, and the consistency metric in the middle. The green line is the all R experiment with Recon. The red line is the no R experiment without Recon. And skill is respect to a no R baseline, and the x-axis is your forecast lead time. So you can see here how Recon directly improved late model track forecasts in all R by 4.3% on average and up to 10%, with at least marginal consistency at all lead times. Next. These are the early model results. They were less consistent with improvement only on days 2 to 3 and 6 to 7. That's what I have highlighted in yellow here. And the MAE skill was also lower at 2.2% on average and up to 7%. Now the y-axis ranges these graphics are different for track. The eventual paper graphics are going to be rerun with consistent y-axes, but I'm in the analysis stage now. Next, please. Now, despite these differences found between the late and early models, the improvement found was both associated with a reduction in the right of track bias from day 3 onward, as you could see here. The along track bias, though, is fairly small relative to this across track bias that you're seeing on this slide, and the differences found weren't as meaningful. Finally, Sibyl et al. 2022 found that the additional recon data assimilated in GFS improved track forecasts. Next. And you can see that here on this slide on the bottom. Now, despite the difference in study period, as I've annotated on the right, what the results suggest is that without this additional data, perhaps in our sample, less track improvement might have occurred. Next. Now let's do some stratification. So first, stratifying the results by year, it reveals that interannual variability was present. Next. While the bias performance was similar across years, the aircraft recon obs reduced this right of track bias. The most improvement occurred in 2023. And this is likely since 2023 had the largest base state errors among the years. So the recon obs were likely better able to reduce the 2023 errors compared to 2020 to 2022. Next. Another way to stratify the sample is by the direct impact of recon obs by initial classification, and you could see that here. It wasn't really dependent on initial classification. Both late and early model forecasts had improvement for both tropical storms and hurricanes. Next. But tropical storms experienced a more immediate impact from the recon obs than hurricanes. It's not clear whether this result is a general result for recon or specific to GFS. I will say that Zwislak et al. 2022 that used HWRF found that recon impacted tropical storms at long lead times and hurricanes at short lead times. So that's opposite to these results. And then recent work that I've done on the overall impact of drop zones on TC forecasts found similar results to that study by Zwislak. Next. So the last way I'm stratifying these track results are by ongoing intensity change. And in doing so, it revealed that the most improvement was found for steady state TCs. And this result is similar to those found in that overall drop zone impact study I just mentioned that was done with HWRF. Next. But also when we stratify this way, it revealed the driver of those consistency differences in the between those late and early model results up top. The recon directly degraded early model forecasts on days 4 to 5, and this degradation was due to intensifying TCs between 2021 and 2022. So the impact of recon obs on VMAX forecasts, now to switch gears here, was different than for track. Next. So in general, if you recall, I said recon obs directly degraded VMAX forecasts, and the impacts here are strongly dependent on the post-processing procedure. Next. On days 1 to 2, the late model had sizable degradation, up to 25%. Again, this is due to that negative intensity bias, as I mentioned earlier. In other words, TCs were too weak. As expected, the early model removes this bias. You could see that on the right, so that the recon obs instead neutrally impacted early model VMAX forecasts. Next. Now, after 48 hours, Recon consistently degraded VMAX forecasts in the late model up to 10% and in the early model up to 5%, particularly on days 3 to 4. Next. So here's a visual of that weak bias reduction. So note that the weak bias due to Recon in the late model on the left, the experiment with the Recon is the green line. It's below the experiment without the Recon, the red line. On the right, that bias is removed by the interpolator. Now, since this negative intensity bias drove the day 1 to 2 results, I'm going to, for the rest of this slide, focus on just 48 hours onward when discussing those stratification results. But before doing that, again, I want to bring in Sibyl et al. 2022 to compare these results to that. Next slide. So as you can see here, these are the Sibyl et al. 2022 results. We found that the additional recon data in GFS V16 improved VMAX forecasts on days 4 to 7 in both the late and early model at many lead times. So this suggests that perhaps without this additional data, the VMAX degradation found in this study would have been even worse. Next. Again, as I said, I'm going to be focusing on the post 48 hours results. And so I'm going to shade out the first 2 days to avoid that distraction. Next. So let's again first stratify our results by year. Again, it reveals that 2023 drove the overall signal, but unlike for track, here the base state errors across the years were similar. Instead, what's driving this degradation found in 2023 were forecasts from Hurricane Franklin when it was a tropical storm and Hurricane Lee when it was a hurricane. Next. When we stratified by initial classification, we found that hurricane forecast drove most of the signal. It was dependent on post-processing procedure, though, so you could see how the late model hurricane forecast had day 3 to 4 degradation, but this hurricane degradation was actually minimized in early model forecasts. And this led to weaker consistent degradation in that full early model sample up top. Now, again, since Sippel et al. Found that stronger TCs had improved Vmax performance with the additional data, perhaps the degradation found in this study would have been even worse without this additional data. Next. And finally, while late and early model Vmax results were more similar when stratifying by ongoing intensity change, in particular, they were more similar, sorry. In particular, Recon obs degraded Vmax forecasts mostly for steady state TCs, but slightly more so in the late model. Again, this could lead to that discrepancy seen up top. Next, please. So to summarize these results, the objective of the work is to quantify the overall impact of Recon obs on TC forecasts in GFS V16 now that it assimilates flight level HD obs as well as additional drops on data near the inner core. Next. So there are 3 different categories of takeaways here. Next. So for track, Recon improves forecasts through reduction of those right of track bias from days 3 onward. Recon is better able to reduce MAE for years with larger base state errors. That was 2023. And tropical storms had a more immediate improvement than hurricanes. Next. For Vmax, Recon degradation for forecasts on days 1 to 2 was due to that late model bias, which was corrected by the interpolator. And Recon degraded forecasts on days 3 to 4, and that was driven by hurricanes and steady state TCs. Next. And then talking about some best practices for data denial experiments here, it's really necessary to stratify impact studies by direct and indirect impacts, because if you combine them together, it could be overshadowing the results. Also, if possible, large multi-year studies are particularly important. These impacts can change from cycle to cycle, TC to CC, and year to year. Obviously, there can be complications with that since a large number of resources are needed to do large sample multi-year studies. Next. So for future work, I'm going to be rerunning the direct sample for only those individual cycles with Recon instead of Recon periods, as I showed here. That'll get even a more precise analysis and assessment of the impact of Recon on TC forecasts. I'm also going to be delving into significant wind radii results. So I didn't show it today, but when looking at those results, the Recon interestingly led to direct improvement in R64 forecasts. And then finally, I do want to look at the remote impacts of Recon on TC forecasts from those TCs and other basins that I didn't talk about today, the East Pac and the West Pac. And next slide, my last little pop-up here is thank you so much for listening. Looking forward to taking questions later.
Thanks, Karen.
Thanks for driving.
Next up, we have Ryan Torn from the University of Albany joining us remotely talking about G4 flight missions and their impact in models.
Thank you. Apologies for not being there in person. It was difficult scheduling wise for me. So once the slides get up, I'll just mention while the slides are coming up that this is work that one of my graduate students, Melissa Piper, has been doing. And this has been submitted as a paper that's under review in weather and forecasting right now. So some of you are aware, the last round of JHT funding, I had developed a product for doing track sensitivity, ensemble-based track sensitivity that the Hurricane Center has used since 2018 to do G4 flight planning. And so what we wanted to do was to quantify the impact of those missions, but without having to go back and rerun them. And so what we're gonna show here is a lot of comparisons of forecasts with and without, a way of evaluating forecasts with and without G4 data. So if you want to go to the next slide, please. So we know that there's a lot of these big error cases are often cases with complex interactions of the storm with the steering flow. We've kind of talked a little bit about them. So one way to reduce those uncertainties is to be sampling them, taking more observations in the regions of them, which hopefully will then have a big impact on the subsequent forecast. Next slide, please. So we know that, speaking to knowledgeable people here, is that for almost 30 years, NOAA's used their G4 to fly around storms, to take dropsondes. Typically, there's 25 to 30 of them in a mission, often in a couple of rings, and then in some synoptic areas of interest around the storm. Next slide, please. So what we wanted to do was go and explore the impact of these G4 dropson data on track, error, and skill during the 5-year period when this ensemble-based sensitivity sampling was used. And so we were testing 2 hypotheses here. One of them, the assimilation of the dropson data is reducing the average track error. And the second one that I'll get into in a little bit in a second is that the assimilation of the dropson data yields additional skill to the position forecast. That we'll talk about how we measure that in a second. Next slide, please. So a little bit on the methodology here. We're considering all storms, all initialization times from 2018 to 2022 in the Atlantic Basin, which overlaps with that ensemble sensitivity period, using the standard NHC verification rules on this. So looking at 0 and 12 UTC initializations, has to be a tropical cyclone at the verification time. And so that yields us 781 total initialization times at 0 and 12 UTC across 87 named storms from that period. And of that 781 initialization times, 69 of them are times where G4 dropson data was used, and that's across 17 storms. So we're going to be looking at the 69 G4 initialization time. So it's a lot like what Sarah was just talking about, the direct impacts, and then comparing them to all initialization times during that period. Okay, next slide, please. So, so we're going to be looking at a couple of different ways of stratifying this. Is that we're going to be looking at the track, error, and skill of the group of initialization times with the G4 data and the group of forecasts that did not. And then we're going to be looking at the difference in skill of the first initialization time that included G4 dropson data for a particular TC versus the forecast that was initialized just before that, 12 hours before that. So looking at, does the introduction of dropson data create a bigger reduction in track error relative to just a generic forecast? And throughout, we use we evaluate the statistical significance using a bootstrap resampling method without replacement. So we're just randomly sampling, subsampling the larger set of cases for a size that matches the G4. So you go to the next slide. So although the strong caveat here is that this is a way of doing a kind of cheap version of looking at the impact of dropson data. The better way to do it is what others have talked about here, where you run an experiment with and without that particular data, but we just did not have the access to the computing to do that. So we're just trying this way. So next slide. All right, so I'm going to show, I'm going to stop and just kind of say what each of these slides are. This particular one, we're looking at mean track error as a function of forecast lead time across the x-axis. Throughout all these figures, though, they're going to try to use a consistent line and color scheme here. So in all of these figures, the solid line is going to refer to forecasts with the dropson data. The dashed line is going to be forecasts without. Blue is going to be the ECMWF ensemble mean forecast, and the magenta is going to be the GEFS. The reason we're using the ensemble is we think that's more stable than looking at deterministic forecasts here. So what you see here, so this is looking at the forecast, all the forecasts that have G4 assimilated at the initialization time, which are in the solid, and then again the dashed are the ones without. For on nearly every lead time, the forecasts with the G4 data is improved, is lower errors than the ones without, but they're statistically significant only from 12 to 36 hours in the GFS, and at the beginning of the forecast and at the end of the forecast for ECMWF. The same is also true of the median in here. I don't have it in here, but just to note that the median is also, this result is also true of the median. If you go to the next slide now, one of the drawbacks of just looking at the G4 data versus just the whole set of Atlantic Basin forecasts is that the G4 data is preferentially at the western end of the basin. There's a different style of tracks. There's a different observation density than other places in the Atlantic. And so what we were trying to do was try to use a skill baseline against Clipper for the set of cases that are G4 versus not G4. So we calculated the Clipper relative skill for the G4 cases versus the non, And what you see is that for both the GFS and the ECMWF, again, there is greater skill relative to Clipper for the forecast with G4 data versus not. Again, GFS skillful in kind of the first 48 hours, and both models much more skillful out at longer lead times as well. So go to the next slide, please. So that calculation doesn't really distinguish between TCs that had a lot of G4 missions versus ones that had maybe one or a few. And so what we wanted to do was assess how much of an improvement came in that first cycle that G4 data was assimilated. You would think, hypothesis would be that that first cycle is just going to have more impact because you've not sampled the storm directly yet. If we go to the next slide, please. So again, we're looking at track skill again relative to Clipper. Now the solid line is the forecast initialization that is with the G4 data, the first one with G4 data for each storm. The dashed line is the forecast that comes right before that. And so you see again an increase in skill for the forecast that occurs with the G4 data versus the one just before that. So indicating that the introduction of the dropsonde data is making for more skillful forecasts. And if you go to the next slide, please. Now we're looking at the difference in forecast skill relative to the forecast before that versus all forecasts that occur in the Atlantic Basin. And so again, here positive values mean a more skillful track forecast than the cycle before that. So you see that the first cycle with the G4 data is producing a more skillful forecasts relative to just a kind of a random forecast in the basin that you're getting from all observations. So again, indicating that that first forecast with the G4 data really benefits from the introduction of that observation, or suggesting that at least. Next slide, please. So we went and did a couple of case studies in here. In that we looked at one of the cases that had a couple of cases that have really large track improvements relative to the cycle before that, and so we were posing the hypothesis that that improvement was coming from changing the steering flow near the storm or changing the initial position of the storm. And so one of the cases we looked at was Hurricane Zeta from 2020. And so if we go to the next slide here, we're looking, these are the forecasts before and after that first dropsonde case. Dropsondes were first deployed. So again, red is going to be the GFS ensemble mean. The blue is going to be the ECMWF. The red line is, the solid line is the first initialization with the dropsonde data. And the dashed is the initialization before that. And then the gray dots here are where the dropsondes were deployed for this particular case. And so if you look at, it's kind of hard to see in this figure, but if you look at the before and after, the before and during dropsonde assimilation, you see that the one with the dropsondes is slower than the one that's before it. And that's closer to the best track, particularly in the Gulf of Mexico. And so it's saying that the introduction of this dropsonde data, or the observations themselves, is helping to slow the storm down and be closer to best track. And you see that there's dropsondes in this case sampling both the Gulf of Mexico, which was indicated at the sensitive region, and around the storm itself. So we'll look at it. If we go to the next slide, we try to do a little bit of diagnosis of where this happens. Here is the track error as a function of lead time, verification time. Again, you see that a lot of that improvement comes in the window that is from 0 UTC on the 27th of October to 12 UTC on the 28th. That's in the period when the storm is over the Gulf of Mexico. So a lot of that, it's saying that a lot of that error reduction is coming potentially from the environmental steering flow around the storm. And if you go to the next slide here, what you see is the steering flow wind barbs for this particular case. With the green barbs are the forecast before. These are at the same valid time. So the green is the forecast before the introduction of the G4 flight data. The magenta is the one with the G4 flight data. And the shading is the difference in the steering flow between those two forecasts. And you see that near as zeta, initially there's some pretty large differences that dissipate, but as zeta moves across the Yucatan and into the central Gulf of Mexico, that's when the differences in the steering flow start to become much larger. The later forecast has a weaker steering flow, which then means that the forecast of the TC position slows down in the forecast. So this is a case where the introduction of the G4 data really does improve the steering flow that the TC is moving into. In the paper, we cover another case in Marco, and there we show that the improvement in the forecast actually comes from the dropsonde data around the storm itself, improving the initial position of the storm, which then leads to the storm going on the either side of a more complicated deformation steering flow. So go to the next slide. This is my wrap up. The dropsonde data had a positive impact on the TC forecast over this 5-year period versus just kind of a generic forecast that did not have it. There's positive impact in skill on that first forecast in which G4 data is initiated. And as you go in case to case, some cases see improvement by improving the steering flow. Some of them are improving the initial position, and sometimes it's a little combination of both. So happy to take questions during the Q&A session, or there's Melissa and my contact information.
Thank you, Ryan. All right, bringing it back to the room, I'd like to invite Catherine Selwood up to talk about dropsondes and their usage in HAFS. Catherine is from the Cooperative Institute at University of Miami, working with HRD.
Hi, thank you. So yes, I've been working at assimilating high resolution dropsonde buffer data in the HAFS model with my collaborators, Al Tuaxoy, Jason Sipple, and Dan Wu. Next slide. Oh, sure.
Doesn't show up here yet.
Oh, okay. Well, you're not missing much. It's just the title. Okay, so thanks. So traditionally, dropsonde have been transmitted and assimilated as temp drop messages, which are these small text files that are limited to a small number of mandatory and significant levels, and until recently contained only a single low accuracy time and location for the entire sounding. So more recently, a remark has been added to the temp drop messages, giving high accuracy beliefs and splash points, which can be used to get better estimates for the intermediate data points. And so this has been used to account for drift in H4 since 2015, and it's really been instrumental in improving the use of intercore tropical cyclone dropsonde assimilation. So now since 2016, NOAA aircraft have been able to transmit high-resolution buffer dropsonde data off the planes, and they contain the full sounding at 1 Hertz resolution and contains exact times and locations for each data point, and it has about 50 times more data than is contained in the temp drop. And the figure just shows a figure from Aberson et al. 2017. It just shows the impact of having good position data. So the black is the actual position data that would be reported in buffer. The red X is the single low accuracy position, and the red dots are interpolated positions, which is much better, but still not as good as having your actual locations. Next, please. And so now that we have all this great buffer data, how do we assimilate it? So it's probably too much. So there's probably going to need to either thin or superob the data. One reason is that the current DA system within HAFS limits sounding data to only 255 vertical levels. And the distance between the vertical levels and dropsondes is about 10 meters, whereas the horizontal separation between observations is more on the order of 50 to 100 meters. And I'm showing a typical P3 track with drops-on locations, and in this case, they're about 90 kilometers apart. And also drops-on data is only assimilated on discrete levels in GSI and HAFS, typically 10 to 20 levels given typical aircraft altitude. So there are a number of ways we can do the superobbing, and depending on how we do this, it would affect the vertical distribution of the data. So on the bottom left, it just shows in blue temp drop data and buffer data for a single cycle that had really good drops-on coverage. And so you can see in the red, there's a lot more buffer data. And so in the middle, if we were going to take that buffer data and superob it onto either height or pressure surfaces, the height surfaces are in blue, pressure surfaces in red. You see that the pressure surfaces would be more weighted towards the lower atmosphere, just given the stratification of the atmosphere. And then on the far right, if we were to compare superobs on height levels to available temp drop observations, you can see not only are there more observations at height, but that the temp drop data is very strongly skewed towards the surface. Next, please. Okay, so when I first started considering this problem of superobbing, I did a very small experiment in the HWARP model using our experimental DA system HEATS. So I just picked 8 different tropical cyclone cases and tried superobbing on using 4 different methods, either 150 meter height levels, 15 hectopascal pressure levels, 10-second time intervals, or trying to match the native model grid. And so here are just some of the basic statistics for that, for the entire forecast length on top and the first 48 hours on the bottom, where you'd expect the drops-on data to have the most impact. And in general, we found that height level data was best for improving the track forecast, which is not surprising since you have more observations at altitude in the steering flow. And for minimum central pressure, actually pressure superobs did a little bit better, which again is not surprising when you have more data closer to the surface. But overall, the height levels performed quite well, which is a good finding since that's the more native coordinate for the drops-on instrument. Okay, so we translated this ability into a HAFS. So I ran a single cycle just to make sure that we were able to assimilate the buffer drops-on data in HAFS. So I chose a case from Hurricane Ian in 2022. And I processed the buffer data both on 150 meter height levels and 15 millibar pressure levels. And so the table shows the amount of observations for each data type. And so you can see there are about twice as many buffer observations as temp drop. And you also see that temp drop has a lot more wind observations than thermodynamic observations, whereas with the buffer data, you have similar numbers of observations. And also the buffer data retains more of the observations. As a percentage of the number of observations, actually temp drop rejects more observations. And then if you look at the RMSE OMB, you can see that the buffer data agrees better with the model on average, and particularly for the height level observations. Next. So with this in mind, we selected a number of cases from the years 2021 to 23. We used the HAFS version 2, the B version of HAFS. I edited the scripts within HAFS so that drops-on buffer processing could be done within the operational workflow to create superobs based on 150 millibar height levels. And for the few cases where, since the Air Force does not always have buffer data archived, we just use the temp drop for those flights. And so here are the cases. Most of the cycles are still running. The only case that is fully completed is Ian. But nevertheless, we'll look at the statistics for the cases that have completed. Next, please. So here we have the track error. Top left is for all the cases combined, and the other three are for the individual storms, which have completed cycles with dropson data. And so you can see that there's some initial trend towards track improvement in all cases, except Franklin, you see some degradation, but I have to warn that it's not really the best case. It was a weak tropical cyclone for the cases that have cycles that have completed, and at this point, the center was not really well defined. Okay, next. So in terms of minimal central pressure, we kind of have a mixed bag. Initially, the central pressure tends to be a little bit better, but then afterwards in the forecast, the results are mixed. So this just points to the need to really complete more cases to get a more robust sample. Next. And then for Vmax, it's pretty much the same thing, although there seems to lean more towards degradation. Hopefully, a larger sample size may give us some more insight into this, or it may lead to a need to have more observations near the surface, but it's a little too early to tell that. Next, please. Okay, so I only have one case where I actually have full data from EMC's forecast to compare. So this is Hurricane Franklin, which so far had completed 6 cycles by this time, only the last 2 cycles with dropson data. Nevertheless, we can compare that to the history runs. And so we can see the O minus B and O minus A for the buffer is in red and temp drop in blue. And unlike our previous results, you see that the departure from the model, both in the background and the analysis, is greater for the buffer data. So, but again, the caveat is there are only 2 cycles with buffer data. There's a similar number of observations for both experiments. So we're not getting more buffer data because at this point in time, the aircraft altitude was relatively low. So it'll be interesting to see what happens in subsequent cycles. Next, please. And so it was surprising to me to see that there was such a dramatic difference in the near surface structure of the storm by assimilating buffer data. As you can see, this is the difference between the buffer and temp drop, and you can some of the difference is due to a shift in position, but you can see that assimilating buffer definitely over intensifies Franklin. So I have the MSLP and Vmax from the best track, the control, and the buffer experiment. And so you can see this over intensification. But one thing that does pop out is the control experiment, although it has a lower MSLP than what was observed, it also has a lower wind speed. So this kind of hints that there may be something going on with the pressure-wind relationship for this case in HAFS. Next, please. Okay, so obviously we need to complete more cycles. And so we're working on trying to work through some of the issues that have held up these cases. But cases are proceeding and we have some solutions. We also may need to run a new control experiment because it's really nice to get full model output to do some more advanced diagnostics. And since the code that we've written actually outputs IODA output as well, we'd like to test the implementation in using JEDI as well. And so some of the outstanding questions is, should we have more levels near the surface? And what's this impact of having more thermodynamic data? And in addition to thermo, we also have height assignments for every data point, which you don't have in temp drop. So what is the impact of that? And then how does the availability of other aircraft operations impact the results? So this is all the ongoing work. I do have a slide about some of the issues we encountered and solutions, but I don't think it's necessary to go through that, just to say that we are working on it and the cases are proceeding.
Thank you, Catherine. Our last speaker for this session is Zhu Lu from the Environmental Modeling Center, talking to us about tropics data and its assimilation into HAFS.
Okay. I'm Shilu, and I'm from Lincoln EMC. So today I'm going to talk about the evaluation of the simulating the tropics observations in the HAFS DA system. So I'm presenting on behalf of the HAFS DA group, and thanks to our co-authors, and special thanks to Isaac and Julia in our bi-weekly discussions, and Nestle for providing the data. Okay, thank you. Okay, so what is tropics? Tropics is short for the time-resolved observation of the precipitation structure and storm intensity with the constellation of small sats. I know it's a lot of words, so I'm not going to read through that. In short, tropics were small, low Earth orbit satellites, and they focus on sampling the tropic storms, which is designed to cover the entire storm's lifespan. So it's kind of a continually sampling the storm, which is very crucial for the inter-core data simulation. So what we have now, just like Jane showed yesterday, when we were trying to do the day impact on JEDI, we have to find different time cycles because there is no, one unique cycle have all the satellite data within this, small DA inner domain. So that's why this data set is very important. Next, please. Yeah. So unfortunately, satellites, the tropics were small satellites that have a relatively short lifespan. So almost all of the tropic satellites were going to expire at the end of this year. So why we still need to do this is because the Tomorrow I/O is expected to launch at the end of this year, and in the future we are going to have those new satellites. And next, please. And those tropic satellites and the Tomorrow I/O satellites share a very similar characteristics between the channels. So whatever we learned from these tropics observations can be applied to the future Tomorrow I/O for operational uses. Next, please. So for the tropics level 1 radiances observations, we are still in the very early stages, and we are still evaluating and implementing it for the GFS. And we have found some similarities in the statistics compared to the ATMS for those tropics microwave sounders. But we are still evaluating the biases across scans. So this is still at early stage. Next, please. So with that is still undergoing development, we are focusing on the tropics level 2 temperature and moisture profile retrievals for this study first. And this is a relatively low-hanging fruit, and I think the University of Utah already proved some benefits of assimilating these observations in their preliminary researches. And the figures here shows the horizontal and the vertical distribution of the tropics were very high density and very useful for the inter-core data simulation. And next, please. So a summary for the goals here. In the short term, we are still focusing on the level 2 temperature and moisture vertical profiles because that's what we have only for now. And in the long term, we'll eventually switch to the level 1 radius data simulation, but we have to first test it in the GFS first, then we can apply it for the HAFS. Next, please. So some brief introduction about the HAFS workflow and the daily capabilities. I think Jane had already covered this in her talk yesterday, so I'm going to skip this, please. Yeah. So let's focus on the level 2 observation characteristics. The figures on the left here shows the horizontal distribution of the temperature observations from tropics at 1,000 millibar on the upper left and 100 millibar in the lower left. This figure shows that the tropics inter-core observations can cover the inter-core regions with very high density and fine resolutions with very unique thermodynamic features of the tropic storms. However, when you look at the MSB on the right lower panel here, you will notice that there is a large inconsistency between the observation and the background, which, the MSB in the temperature field can be up to 60K, which is not acceptable. So next slide, we will do some preliminary QC, like pre-processing, to filter out the observations. So what we are currently doing is a 10 kilometer horizontal seaming and a 50 millibar vertical seaming. And also we apply some smaller gross error check so that OMSB can be constrained within the 10K range. And you notice that in the lower panel here is what we got after the QC. And the finer structures in the core thermodynamic structures can still be maintained while the data quality is much improved. So next, please. And also based on that, we are going to estimate the observation errors using the derivative method, using the OMS-A, OMS-B, and the black line on the left is for temperature and the moisture on the right. Next, please. And with that, we started to do some preliminary data simulation tests. So the figures here shows the horizontal moisture field at 350 millibar. And upper left is observation. Upper right is the tropics DA, and lower left is the control experiment. As you can see that the observation clearly have more finer inner core structures, which is lacking in the control. And the control is showing some weak or dry biases. And this is especially apparent when you look at the absolute mean moisture field in the lower right panel here. There is a kind of like a weird dry core in the control experiment, which is likely the reason of the spin down issue in the intensity prediction for the control in cyan line on the right. And when we assimilate those topics data observations, we clearly improve the inner core structures. Also, this dry core feature is gone. And also, we have a better intensity predictions consequentially. Next, please. A similar story happens in the temperature field. So this is the 350 millibar temperature field, where we assimilate the tropics observations, clearly benefits the inner core summer temperature field. And we see that this upper level warm core is reduced. And next, please. And also, when you look at 600 millibar, where the control shows kind of like a secondary low level warm core is also reduced in the tropics DA experiment. So these figures shows us that the simulation of those tropics observations indeed help us to improve the inner core thermodynamic structures. But next, please. When we do the forecast, so the forecasts were only one storm, Hurricane Lee in 2023, and it was based on the HAFS version 2.1, the parallel experiment configuration, but we are taking the IU off to maximize the DA impact. And the upper panel shows the track. The lower panel is for Vmax. Left is the error, and the right is the relative skills. And you can clearly see the cyan line is, or the magenta line is for the tropics, and the cyan line is the control. Clearly, there's kind of like some slight improvement in the track for long term and then kind of mixed for the intensity. But the most severe issue is in the short term. There was a degradation for almost all metrics. So what happened? Next slide, please. If we look at the individual cycle predictions, first, if you connect next, please. Yeah, first of all, we noticed that there's kind of like a strong biases for, when the intensifying cycles, and weak biases for the early cycles in the control, which was, much more improved in the magenta line on the DA for the right column here. But we also noticed that, next please, this kind of like weirdly strong initial Vmax happens in the DA experiments, which accompanies by the severe spin down issue that is significantly degrading our short-term intensity predictions. And next, please. So we are trying to figure out why. And this is with one example where those significant spin down happens. So if you notice that the DA analysis pattern, this is so weird. I mean, you have this very super strong gradient in the wind field and some dipole features in the pressure field. And this is something we repeatedly seen in the HAFS version 2 when there is an inner core data simulation come in. So what exactly happened? If you go to the next slide, please. Yeah, so I choose easy, kind of like extreme situation. So if you click next, please. Yeah, so the blue star is where the best track location should be. And the red star the red dots is, ideally we want the ensembles to be in those places. But if you click next, the green dots is what actually those 6-hour ensemble forecasts were. You can see there's a large location shift within just 6-hour forecast. And this kind of shift in the ensembles is kind of like making the ensemble under dispersive. Of course, this is not ideal for the intercore data simulation. That's why we are seeing those weird patterns in the, when the TDR, or in this case is the topics intercore data simulation comes in. And the location issue is, it's easy to visualize, but we can imagine there's more differences when we're using the GDAS ensembles. Those GDAS should have, relatively larger storm sizes, weaker intensities. Those were kind of like features that is not very good for the intercore data simulation. So if you click next, and the right column here is simply we are using a 6-hour co-started HAFS ensemble. And after relocation, correcting those ensemble location issues, clearly you have a much better analysis with much smoother, wind and pressure fields. Of course, there's still room to improve because we are using very preliminary scening, QC techniques for the topics data simulation. But this illustrates the point that we definitely need a better, covariances to digest those high resolution intercore observations. And I mean, relocation is one thing. Maybe we try, hourly data simulation. There's too many possibilities, but GDAS ensemble is definitely not a very good choice. Next, please. So with those, relocated HAFS ensembles, the green line here shows clearly a significant improvement in the short-term intensity. And there's still some gap, but that's because some very weak stages at the end of the storm life cycle where, VR might not still working because the storm is decaying and there's not enough structures there. And next slide, please. And when we expand the sample size for Hurricane Idalia, similar story happens. So when we simulate the intercore data simulation with vortex relocation, the green line shows significant improvements in the analysis, especially intensity. If you can see this, it's now positive. And for the biases, it's almost neutral. However, we still notice there's a kind of like a short-term degradation between R6 and R36. So what happens is next, one of the issues is because of the observation error we estimated were from Hurricane Lee cases, which is significantly different from the characteristics from Hurricane Idalia. So what we are proposing is using an adaptive observation error profile that's kind of like averaging the statistics from the current year cycle and the previous statistics so that it can consider the storm evolution and also the different storm characteristics. But this is something is still ongoing. Next, please. Okay, so I'll keep it this short summary here. So for the level 2 observations, the temperature and moisture profiles, it can be assimilated into the HAFS version 2. And we found the benefits in assimilating them in the intercore thermodynamic structures. But some degradations or negative impact were found in the short-term predictions in our preliminary experiments. So one big issue is ensemble covariance need to be better. And second one, we need to improve those observation error estimate. But also there's kind of like many other possibilities. For example, we need to tune our scenings because this is kind of like a random configuration here. And also we may want to try turn off the vortex initialization because we are still modifying storm intensity based on the TC vitals when we have those continuous sampling of the inner core. That may conflict with what is ideally produced from the model. And for the level 1 readings, we are still waiting for them to be ready for the GFS first, and then we can start to investigate for the HAFS version 2. Okay, thank you.
All right, well, let's throw it to the room to see if we have questions for any of our presenters. Got my co-host Jason Sippel here to help run. All right, I see Kevin here.
Thanks you for that presentation on tropics. Just curious for the level 2 products that you're using, and I lost sight of you. I don't know where you sat down. Oh, right there. Okay. So do you know, because I know Wisconsin was doing a lot of work on mirrors to develop the retrievals for tropics. So I assume you've mentioned that's the one you mentioned that you're using for ingesting for the assimilation, the mirrors level 2 products.
Jason, can you give him the mic to respond? Thank you.
Yeah, so we currently got them from the GES disk. So the official site.
Okay. So my recollection was that they were using the GFS forecast as the a priori for that retrieval. So just like a word of caution, I don't know if there's any impact, but the 118s are obviously very difficult to assimilate or do retrievals, particularly when there's clouds and precipitation. So essentially, if there's no signal, the retrieval is going to look a lot like the background field. So you may end up assimilating the GFS background. So I don't know if you've looked into that at all to understand. Maybe the O-Bs, they look pretty broad, so it looks like there are probably some differences, but yeah, I just might want to keep an eye on that. Also, I don't know if you've done any like control studies, maybe looking at ATMS retrievals and trying to assimilate those and see how they compare with the tropics. May help you calibrate and configure like the observation errors and things like that. So thanks.
Thanks. Very good suggestions.
So we've got several questions online for Windborne. So if you want to unmute your mics online and ask them, I know we have one from Pete and one from Mark Vincent. Pete Black, if you're up. If not,
This is Mark, if you can hear me. My question to Todd was, is the Windborne data coming in through Synoptic in real time and in the format, proper formats?
Thanks, Mark. Yes, the Windborne data is going through Synoptic into the NCEP data tanks as well as the GTS, or currently a subset of that is live and flowing through.
Thank you.
Yeah, Todd, my quick question was, where exactly are these new upsigns being manufactured? Is that something being done in-house, or is that contracted out?
The dropsons are being manufactured in-house, as are the balloons actually, and so they're very custom to the system itself and being manufactured in-house with some off-the-shelf parts going into them.
I'm really interested in that, as several other places are doing the same thing as the Japanese and in Taiwan. They're developing their own sons as well. So interesting to see how that works out.
Yeah, there's certainly opportunity to learn and collaborate in these areas. So thank you.
we had one more online that asked, can we navigate the balloon to follow a hurricane?
So in terms of navigation, yes, it can certainly be navigated, and it basically, because you have vertical control of the balloon, you can get ascend or descend to levels where the prevailing wind or the winds will push or propel the balloon towards the target of interest. So you can build trajectories, and we do that fairly automatically. So it's possible to navigate towards cyclones or any target. Given that the flow would support it. Obviously, you can't go upstream if there's no path, but yes, you can do that. It is possible to do that, and we have done that in the past. Some of the challenges are to remain outside of heavy precipitation, but there often is a path, especially at high levels, to do that. So, thanks.
Are there any more questions in the room?
Hendrik from Weather Service. I have actually a little bit more general question, not just for this group, but looking at it for the last 2 days. Historically, we've always been looking at track and intensity, two very integrated values of any tropical cyclone. We see more and more high resolution data. If you look at what the satellite looks now compared to 20 years ago, it's a completely different thing. I heard a few people making statements about, yeah, the track and the intensity are not that good, but look at the structure, it looks so much better. Isn't it time that we actually start looking at some more advanced metrics to actually measure these things? And just thinking of that across different bits and pieces and fields. If you do a bias and an RMS error in general for anything, you're going to favor the smoother solution rather than the more realistic solution. So in the ocean, we went to Taylor diagrams for that to look at also whether the variance of the signal is captured. Of course, with our performance diagrams that we're looking in the atmosphere more, it helps a little bit. But I would really suggest that we start looking at whether or not our models capture the variance of what's going on, and not just these really big, almost old-fashioned Gipper measures, if for those of us who are old enough. So, older than me.
All right, handing it over to Frank, and then I see Gus's hand up.
Frank Marks, HRD. So this is for Zoo. One of the things about tropics was it was designed to improve rainfall. And what I'm thinking is you're assimilating the radiances into the model, and you're changing temperature and humidity. That impacts the microphysics. Have you evaluated, to go along with Hendrik's comment, have you evaluated the rainfall from the model versus the estimate from the satellite? Another thing is you could test the sensitivity of the microphysics to the radiation, and I think this is a big area. I was once a tropics COI, so I know what they're trying to do, and all the things we said we were going to do was mainly look at track and intensity, but this is a perfect opportunity to look at the microphysics code. You're using Thomson, right? But you're changing the thermodynamic profiles. That's going to have a big impact on microphysics, but does it affect the rainfall? I don't know. So something to look at.
Yes, thank you. This is a very good suggestion. We are just starting this research. So yeah, definitely we will eventually focus on the precipitation.
Yeah, hi, Gus Alaka, HRD. To Hendrik's comment, and just in general, I mean, I think we've talked about it a couple of times, but this is why investing in a high resolution reanalysis is something that's sorely needed. I mean, I think we've gotten a lot better observation-wise from the satellite at sort of having a better understanding of what's happening near the surface, but what's happening all throughout the atmosphere, right? And I think, you know, it really calls for the investment in a reanalysis in order to really get to the bottom of these you know, questions, or at least partially answer them.
Yeah, I'm looking a little bit from a distance too, because when that question was asked yesterday about higher resolution analysis, Vince Cardone, Ocean Weather, those guys have been doing something there for 25 years by taking the, yeah, well, Vince passed away 5 years. But even there, that's a step the right direction. But the whole approach that Ocean Weather is doing is still with a Holland style wind field. And so we have that bifurcation a little bit, people going, I go high resolution, high detail, but still use a Holland style wind field. And those who are seeing the band structures, they want to do something with that. And so we need to kind of figure out what we want to do with that higher resolution thing. And I mean, as a sailor and as a guy who was stupid enough to go out sailing in tropical storm force with a 1950s wooden sailboat of 26 foot. And yeah, they're the best boats ever built, but that's another story. And living on the Chesapeake and seeing a few things coming by. For instance, storm surge, when I was sitting with Isabel on our beach, the water was at a certain level. A rain band came through, and every rain band, the water went up 4 inches. And so the whole issue of the fact that there is so much more going on, just an example, just showing that I'm not claiming I'm a meteorologist, but just showing that there is so much of the physics going on with the details that we don't see even in an ocean weather style analysis. So I think we need to go that extra step in looking at the actual land structure of the whole system.
Thanks. We have a comment and a question online from Dave Jones. Dave, do you want to?
Sure. Can you hear me okay?
Yes, we can.
I was just wondering that when we look at these data denial experiments, you take certain things out, see how the models run, and you say, oh, it's worse, when we take this data out. Has there been any thought to extending that input into how that might impact the National Hurricane Center forecast? I know they look at a lot of different data, but if we can take the data denial experiments one step further and see how, if this forecast were followed, it saved the evacuation of this many people, or it led to the protection of this much property. I'm wondering, that way data denial experiments could make a lot more sense to the layman out there that might be in, high positions to make decisions. Thanks.
I can comment a little bit, on that. That's a great question, a really great point. I know that there's some work being done at the University of Miami to look at the socioeconomic benefits of the augmented aircraft observations. Another way I wonder if we could get at that is by doing some experiments where we take, NHC forecasts and then stratify that by those that had, Recon data and those that didn't have Recon data. Jason Sippel and I played around with that, I don't know, like a year or something ago, but then had, other things came up. So we haven't looked back into that. I think some of that work might be being done, though, by folks at NHC. You guys in the room correct me if I'm wrong with that.
Well, sir, that's what Ryan Torn, he looked at it specifically for the G4, right?
Right.
That's essentially, what he's doing.
Yeah, my question really is that I know Ryan's doing great work, but how would this impact? It's almost like maybe a test bed or a hot sort of thing where you deny the Hurricane Center forecasters that data as well. So they have to make decisions based on that data denial. And how does that impact the watch, warning, advisory, storm surge, things like that? Because that's where the rubber meets the road with outside of this room.
I mean, that's difficult, right? So, I mean, you can quantify it in terms of like, okay, you take the data out of GFS, for example, or add data GFS and then, rerun the consensus, right? So that's one thing. But if you're denying the actual data to the specialist, there's no way to replicate that. In that's just the real world. They have the data. So there's two different aspects of how this data is useful. For example, with the reconnaissance data, they have situational awareness, and we can't replicate the situation where they don't have that data. I don't know how to even begin to quantify that.
Yeah, I'm thinking more about a experimental setup where they wouldn't have that information in the model output. But anyway, it's a conversation down the road. I'm just looking to make they're great results, just looking to make them more applicable to people who have to make budgetary decisions in the future. Thanks.
Hey, Dave, this is Aaron. I just want to say it's an interesting thought exercise, but like Jason said, if you show it to them one way and then show them a different way, you've biased the second way. I don't know if we're going to ever be able to remove that short of using different forecasters completely isolated from one another, which again is going to have differences of opinion. So I think that's something we'd probably have to table for future thought. But
yeah, fair enough.
Kate, go ahead.
Yeah. So Kate Musgrave, Sierra. The closest you could probably get there is that most of these models are in the consensus techniques. So you could actually rerun the consensus techniques and show the differences in those. And that's probably as close as you'll get to the official forecasts, because otherwise the subjectivity of the different forecasters. And honestly, even when you try to do it in a retrospective fashion, which has been done for various things in the past, memories are long. So even if you hide which storm it is and where they're pulling from, generally from the information that's being provided, they can still tell, and they still remember what was there originally. So, but the consensus techniques might be an option there.
Yeah, this is Wallace from the Hurricane Center. So I was just going to add to what Kate said. And another proxy for that would be looking at the ensemble spread. And, you know, by getting more obs, we're trying to constrain the uncertainty. And if we can prove that the spread is reduced, you know, that would be a proxy for increasing confidence, maybe shrinking warnings, things like that. Oh, and real quick to Hendrick's point, yeah, absolutely. Like the two-dimensional surface wind field is what causes damage from winds. So we need to do better at verifying that.
Jason,
and get a little more sophisticated. The traditional metrics, they're very simple. They're one-dimensional. I think that's why we've stuck with them. But yeah, I think we need to expand by a dimension or two.
We've got one last comment from Gus, and then we're going to head to lunch.
Yeah, a little bit of a different thought here, but you know, one of the things that Sarah and Jason's work found in looking at HWRF is these indirect impacts from all these observations. And I think as we go to, you know, modeling systems that hopefully have high resolution over multiple storms, whether it's a multi-nest or whatever, it's important to remember that these data impacts can extend far beyond just the storm that they're even being measured in, especially for G4, which is sort of in the synoptic scale environment. So I think we also have to be a little bit forward thinking in terms of how these observations don't only impact the storm in question, but also storms that are downstream perhaps. And just some food for thought, something to think about over lunch, I guess.
Let's thank the speakers one more time.
And let's thank those session chairs, Lisa and Jason, especially Lisa, because she did most of the work.
And we'll see you
I
later.
do have one announcement I want to make before everyone funnels out for lunch, please. And that is the first session after lunch on the hurricane near real-time experiments and the HERC Ensemble 2024. We had to flip the order of two of the talks. So Tim Marchuk and Zach and Jai's talk are going to flip time, but we're still doing all of them. And with that, please go off to lunch and we will be back at, I believe it's 1:15 sharp. Thank you.